So in the last lecture, we were considering fold bifurcation again. So we had, let's go to bifurcations. Bifurcation theory. So we consider x dot equal to a flow, one-dimensional flow with parameter c. Then we say f 0, 0, or let's say xc equal to 0, 0 is, we assume that it is non-hyperbolic. Equilibrium. And if it's non-hyperbolic equilibrium, we can consider what we checked is second order approximation. And second order approximation can be reduced to derivative of f over c at 0, 0 times c plus half of second derivative over x at 0, 0 times x squared. So this is what we decided. And from here, we found normal form for fold bifurcation. Again, so everything was fine, but in our analysis, we were presuming that we can get this to come to this second order approximation, which means that derivative over c at 0, 0 is not 0, and the second derivative over x at 0, 0 also non-zero. And these are called non-degeneracy conditions for fold bifurcation. If, let's say, a of these two is 0, then we're in trouble. Then we should further extend our analysis. And what we'll do now, we will consider the case when derivative over c at 0, 0 is 0. So degenerate case. If this is 0, then f of xc at 0, 0 should be represented as as a second order approximation, which will be half of second derivative over x times x squared plus mixed derivative times xc plus half of second derivative over c times c squared. So what we can say, we can put it like this. We will call this b, we called it b before. This will be called e. This will be called d, sorry. And this will be called e. Therefore, we will have x dot approximation to our equation, x dot equal to bx squared plus dxc plus ec squared. So this is, and we can assume that b and d non-zero. Let's put it like this: b non-zero, d non-zero. These are non-degeneracy condition. Conditions for transcritical bifurcation. But I will come to this later. For now, assume that E is 0. So I will come to this point later. But if E is 0, then x dot will be equal to bx squared plus dxc. And now we can make substitutions. So our substitutions are x tilde equals to p by absolute value times x, and c tilde equals to d by absolute value times c. This kind of substitution is very similar to what we did for when we analyzed fault bifurcation. And when we use these substitutions, you can check it. Eventually, we will come to this equation: x tilde dot equals to b over absolute value of p times x tilde squared plus d over absolute value of d times x tilde times c tilde. And so b over absolute value of b is either plus 1 or minus 1. D over absolute value of d is a plus 1 or minus 1. So provided b and d are non-zero, which we discussed before. Therefore, we will have x tilde dot equals to plus minus x tilde squared plus minus x tilde c tilde. Or after changing our notations, we get x dot equals to plus minus x squared plus minus xc. So this is called normal form for transcritical bifurcation. Let's consider case. Let's consider case when x dot equals to x squared plus xc. Yeah. So this case plus plus. In this case, we have equilibrium. X1 equal to 0 and x2 equals to minus c. And if we possibility, derivative of f over xc is 2x plus c, and derivative of f when x equal to 0 equals to c, and derivative of f when x equals to minus c will be minus c. So this means one of them is stable and another is unstable. And who is stable, who is not, depends on the sign of c. Let's plot it. So we have so x equal to 0, which is unstable when c positive and stable when it's negative. So therefore I will put it like this. It is stable and unstable here. It is c and this is x. And x2 equals to minus c. It gets down. It is unstable here and stable here. So this is the case plus plus. And we can consider 3 other cases. Next case is, let's say, minus minus. For minus minus case, x equal to 0 will be unstable when c is negative and stable when c is positive. And x equal to minus c will be stable here and unstable here. Next case is when we have, say, plus minus. If we have plus minus, then x equal to 0 is unstable when c is negative and stable when c is positive. And x equal to c is stable here and unstable here. And last case, minus plus. So this is stable here, unstable here, unstable here, and stable here. So Cx, Cx. So this is all 4 cases. And I would suggest you to check all 4 cases and draw bifurcation diagrams after you make your own analysis. For now, I am getting back to the condition, which is second derivative over c at 0, 0 is 0. So this is, in fact, it should not be like this, but it appears to be this case for special case, which is quite commonly appears x dot equals to x times g of xc. So this, it is flows which occur frequently. So let's consider this kind of flow. So for this flow, 0, 0 is an equilibrium. Let's consider, so what we have here, f of xc is x times g of xc. Let's consider derivative of f over x at 0, 0. So the derivative is equal to x times derivative of g over x at 0, 0, which is 0, plus plus 1 times g of 0, 0. So I paused it somewhere. Anyway, this not sure at what point I stopped recording. So derivative of f over c equals to 0, it shows here. And this means that we don't have fault bifurcation. Second derivative of f over c, it's x times second derivative of g, but x at 0 is 0. Therefore, we have second derivative of f over c is 0. And in our second order approximation, e is 0. And this way we get back to what we have considered so far, x dot equals to bx squared plus dxc. Yeah. And so indeed, for many flows, E is not 0, but this is not 0 case Okay, it's a bit longer study of this, and it can result to two cases. One is non-local case, when, for example, if C is 0, 0, 0 is equilibrium. If C is non-zero, we don't have equilibrium at all around 0, so it's not local behavior. But if it's local, then we can find substitutions such that we will again get transcritical bifurcation. I am happy to show it on Wednesday online session. Now I want to go to the last third bifurcation, which is Pitchfork bifurcation. So again, let's look at second order approximation of our flow around 0. And now I will use slightly different notations. Instead of using B, D, E, and so forth, I will use A's, like A1 times C plus A2 times X squared. So I need it because I will have many more terms. A3 times XC plus A4 times C squared. So this is second order approximation. So what we considered so far, so A1 is 0. It is so it's degeneracy condition. Degenerate fault, I will put it like this. We don't have fault bifurcation if A1 is 0. And now assume A2 is 0. So this is degenerate condition for transcritical bifurcation. So this was important that A2 is not 0 to have transcritical bifurcation. And if under these two assumptions, X dot will be equal to A3XC plus A4C squared. And now here we have anyway we have degenerate case, because when C equals to 0, we have any X is equilibrium. So this is called non-local behavior. And this means that we need to go to third order approximation. Okay, and if we get to third order approximation, I will just straight away go to two notations in terms of A's. A3XC plus A4C squared plus A5X cubed plus A6X squared C plus A7XC squared and plus A8C cubed. Now, so in here we have two first order terms, this two second order terms, and everything else is third order. considering third order approximation makes sense if at least one of third order terms is of the same order as one of the second order terms. Same range of values, let's put it like this. And now what we can say. So what we know, that x very small, c is very small, and if these two guys are small, then for example A8c cubed is much smaller than A4c squared and can be ignored. And same with A7xc squared, also much smaller than A4c squared, for example. And on the other hand, A6x squared c much smaller than A3xc also can be ignored. So what it means, we can remove this, and remove this. And now we will have x dot equals to a cubed xc plus a4c squared plus a5 x cubed. So this term, cubic term, should be of the same order as either this or this. And we can't compare directly. Well, probably we can. If x cubed is of the same order as c squared, this means that c is of the same order as x to the power of 3 over 2. And this means that xc of the same order as x to the power of 5 over 2. And therefore, a3xc should be more than a5x cubed, and this means that a5x cube should be ignored. And this way we get back to second order approximation. This is wrong. Therefore, the only option we have is if xc of the same order as x cubed, which means that x squared is of order of c. Then it is fine. And in this case, it means that a4c squared is much smaller than a5x cubed and can be ignored. And therefore, we get to this approximation. X dot equals to a3xc plus a5x cubed. So this is to what we got. And now we make substitution. Substitution like this: x tilde equals to square root of absolute value of a5 times x, and c tilde is absolute value of a3 times c. And after using this, from here we get x tilde dot equals to a3 divided by modulus of a3 times x tilde c tilde plus a5 divided by modulus of absolute value of a5 times x tilde cube. Or after changing notations back to x and c without tilde, we will have, and noting that a3 divided by absolute value of a3 is plus or minus 1, and a5 divided by absolute value of if I have plus or minus 1, we will get x dot equals to plus minus xc plus minus x cube. And this is normal form for Pitchfork bifurcation. Pitchfork bifurcation. And now we can consider simple case. X dot equals to xc plus x cube, which is case plus plus. And for this case, we will have equilibrium. X equal to 0, x1 equals to 0, and x2, 3 equal to plus minus square root of minus c. And which exist if c is negative. And about stability, derivative of f equals to derivative over x is c plus 3x squared, and derivative of f at x equal to 0 c equals to, we can see it will be c. So stable if c negative, unstable if c positive, and derivative of f for x that was x1, so x2, 3 equal to plus minus square root of minus c. This will be equal to minus 2c. And this is stable if c positive, unstable if c is negative. And the bifurcation diagram in this case looks like this. So 0 is stable up to 0 and unstable sorry, this is cx, and x2, x3 both unstable and exist when c is negative. This is case plus plus. Next case, which is say minus plus, it will look like this here: unstable, stable, unstable. Third case. Third case when minus, plus minus, plus minus, stable, unstable, stable, cx. And last case, cx minus minus. Unstable, stable, stable. So, and these cases, these two cases, called supercritical, Pitchfork, and two other cases, plus, plus, and minus, plus, they called subcritical. Pitchfork. So difference is that these extra two equilibria are stable for supercritical and unstable for subcritical. So this is pretty much complete classification of bifurcations. There are no other bifurcations which can be observed in flows.